But what if there's a breakthrough? Something that completely reframes how we can approach these, moving past those old limits. Okay, let's unpack this.
It's definitely a challenge, a big one. Using classical methods for these high-degree polynomials, like the degree 17 example, it's tough. Your traditional approaches, things like Newton's method, they fundamentally rely on numerical approximations. You're basically making educated guesses, getting closer and closer, hopefully. But you never quite land exactly on the true value.
Right, like throwing darts in the dark. You might get near the bullseye, maybe even hit the board. You can't guarantee you hit the absolute center.
Exactly. And that's the core issue with numerical approximations. They are inherently prone to errors. You get rounding errors creeping in. And critically, they just can't guarantee exact values. It's not a minor detail. Plus, for centuries, there was this major theoretical roadblock, Abel's theorem.
Ah, Abel's theorem. I've heard of that. That's the one about radicals.
That's the one. What's fascinating here is that Abel's theorem basically stated, quite fundamentally, that certain polynomials cannot be solved using only basic arithmetic and roots, square roots, cube roots, what mathematicians call radicals. So this traditional view drew a pretty firm line in the sand. It really limited our ability to find those truly precise, exact solutions for many polynomials.
Wow. So for ages, the thinking was just, nope, hit a wall, can't be solved exactly. Yeah, a huge limitation. So where does Ezouidi's theorem come in? How does it start to, nudge that wall? Here's where it gets really interesting. How does this new theorem sidestep something that sounds so fundamental?
Well, it's a totally different paradigm, a revolutionary approach, really. The fundamental difference with Ezouidi's theorem is that it allows for deriving exact symbolic solutions. Think about pi. A numerical approximation is 3.14159, but the exact symbolic representation is just perfect, true.
Right.
Ezouidi's theorem gives you answers like, say, x equals the square root of 2 plus 3 times 8, where I is the imaginary unit. These are precise mathematical expressions, not decimal approximations, not guesses. And here's the kicker. This method actually excludes all classical methods, including the constraints of Abel's theorem. It demonstrates that even polynomials whose roots aren't expressible using radicals can still be solved exactly.
Okay, wait, that's a pretty bold claim, excludes all classical methods. How does it manage to just walk around something like Abel's theorem?
Because it operates in a completely different mathematical framework.
Yeah.
It's not attempting to find solutions using radicals in the way Abel discussed. Instead, it's constructing symbolic representations that are the exact solutions themselves. The method doesn't fit into the box Abel described.
Ah, I see. So it's not breaking Abel's rules, it's playing a different game entirely.
You could put it that way. The core of the theorem involves a recursive process. Imagine maybe like a set of nested Russian dolls or mathematical puzzles, where solving one small part systematically reveals the information needed for the next part, building up the whole solution. You can put it that way. The core of the theorem exact values of the roots. It does this by breaking the polynomial down and solving for its components symbolically. And crucially, this avoids all the errors that inevitably come with numerical approximation. Every single step deals with exact symbolic values.
So if I'm getting this right, it's like the coefficients, the numbers within the polynomial are themselves being solved for symbolically as part of the process. You're building up the final root piece by piece without ever resorting to numerical guesses.
Exactly. That's the beauty of it. It guarantees you're working with pure, unadulterated mathematical precision from start to finish. Now, to make this less abstract, let's talk about that specific polynomial used to demonstrate the theorem, the 17th degree one. And believe me, you don't want me to read the whole thing out loud. It's enormous. Coefficients in the millions, takes up lines and lines, a real monster for traditional methods.
Yeah, maybe spare us the full recital, but can you walk us through the sort of the conceptual steps? How does Ezouidi's theorem actually grapple with that beast?
Absolutely. Conceptually, the process takes this massive polynomial and rewrites it using what are called symbolic coefficients. Think of these not as approximate numbers, but as abstract placeholders, like variables that represent exact values. These values are derived directly, recursively, from the original polynomial's coefficients. So through this recursive calculation, the theorem figures out precisely what each of these symbolic coefficients has to be, For instance, in that 17th degree example, it turns out that several of these symbolic coefficients, we call them SSR up to S6R, and then SSR up to S to 14, they are revealed to be exactly zero, just zero.
Okay.
But others are non-zero, and they're exact values. Like a set of R turns out to be precisely minus 204,309 times 17 raised to the power of 8, a huge specific number, and S15R is even bigger. 552V4 set of 9 times 17 to the power of 16. Again, an absolutely exact value found, no guessing involved.
That's incredible. So the theorem is uncovering these exact, almost hidden numerical relationships deep inside the polynomial structure. So how do these spherical values lead you to the actual roots?
Well, once you have these exact symbolic coefficients, they reveal a much simpler structure hidden within the complexity. For our monster polynomial, once you substitute these CR values back in, the whole thing simplifies dramatically. It becomes bx multiplied by 16 plus S7R by 8 plus S15R, and all of that equals 0.
Wow, that's a huge simplification.
It is. And right away, this gives you one perfectly exact root, x equals 0. Because if x is 0, the whole expression is 0.
Makes sense.
Then you're left with solving the part in the parentheses. By 16 plus S7R by 8 plus S15R equals 0. This looks like a quadratic equation if you think of by 8 as the variable. The theorem provides a way to solve this, again symbolically, finding values for x in the 8, and then taking the 8th root. The final roots involve these CR values and often complex numbers expressed precisely, maybe involving things like 2i and 8. They aren't neat little integers or simple fractions, but they are exact mathematical expressions derived systematically. It's really a testament to the power of the recursive symbolic approach.
Okay, so let's pull back a bit. What does this all mean, big picture? We've gone from this idea of certain polynomials being fundamentally unsolvable exactly, limited by major theorems like Abel's, to this method that seems to just deliver the precise symbolic answer.
That's the core takeaway. The absolute strength of Ezouidi's theorem is its precision. It completely sidesteps numerical approximation. The roots you get are exact. They aren't vulnerable to the rounding errors and the inherent limitations you find in numerical methods. This approach guarantees that we can find the roots exactly, even for these really high-degree polynomials that classical methods just couldn't handle if you wanted the perfect answer. And that precision, it comes directly from the theorem's recursive structure. It allows for the systematic step-by-step derivation, again, with absolutely no approximations along the way. It really feels like a new chapter for solving these kinds of problems.
This is clearly more than just a neat trick for mathematicians. We're talking about a theorem that tackles problems genuinely thought to be unsolvable in this exact way. It really does redefine the boundaries of what's possible. It makes you wonder, doesn't it? What other mathematical mountains, other problems deemed unsolvable, might actually yield to new ways of thinking, to structured, symbolic approaches like this one? And what could cracking those problems mean, not just for pure math, but maybe for physics, for engineering, finance, even fields we haven't conceived of yet? How might this shift our fundamental understanding of what is ultimately knowable?